Hi, welcome to this talk about loop transformation new in OpenMP 5.1. I'm Merkel Kruse, working at Argonne National Laboratory on the exascale computing project. Let's first go into a preface about the history of compiler optimization hints. One of the first compiler hints introduced was probably by the Cray compiler in forms of the IVDEP, which tells the compiler that a loop is allowed to be vectorized. This was copied by multiple other compiler vendors such as HEI, AP, Intel, which also copied the pragma IVDEP and allowed it in their own compilers. Recently, in GCC 9, it was also introduced in GCC. But GCC insists on a namespace prefix GCC, since technically this is not part of any standardized language, but a compiler extension. The Cray compiler later introduced this as well in form of the CRI namespace, but it's just optional. Other compilers, such as Microsoft compiler and Clang, also provide similar pragmas, but have completely different syntax here. In addition to that one, some compilers support multiple of those pragmas with slightly different semantics, such as the Intel pragma vector and pragma SIMD, which not only tell the compiler that vectorization is allowed, but also instruct the compiler to actually do the vectorization. The problem with this, in addition to the lots different syntaxes, is that the semantics of what these pragmas actually are doing can be quite different. So for instance, Cray original IVDEP implementation is implementation dependent. It basically says that the compiler will detect some dependencies, such as reductions, but is allowed to ignore all the other dependencies. This makes it sensitive to the analysis power of the compiler. So if the compiler, like newer version, other versions, older versions, does not detect a reduction, it will just miscompile the application. This basically ended with OpenMP 5.0, where OpenMP added a standardized vectorization directive in the form of a pragma OMP SIMD, which is standardized, same semantics, same syntax, same semantics across all the compilers which claim to support OpenMP 5.0. This is being used by itself, so even if your application uses some other means of parallelization, for instance, using the C++ library for threads, some projects still use the pragma OMP SIMD directive to tell the compiler, hey, vectorize this loop, since this is not part of any host language. As a consequence, Clang even supports the SIMD only mode. So if you pass the OpenMP-SIMD option to Clang, it will accept the OMP SIMD directive, but ignore all the other directives and does not require it to link against the OpenMP standard library. So this is a relative success. Why don't we also do this for other directives? For instance, lots of compilers, as shown here, allow already an Unroll pragma. But again, the syntax between all these compilers are quite different, although the semantic difference is not a problem because unrolling usually should not affect the program semantics. So with OpenMP 5.1, we also introduced an Unroll directive. Again, standardized, same semantics across compilers, which are going to implement OpenMP 5.1. The effect of this depends on the mode. So for instance, we have a clause, a full clause. If you specify pragma OMP unroll full, then we do some full unrolling. In that case, the number of iterations must be known to the compiler, and it will just remove the compiler and replace it with the instances of the loop bodies. The other mode is the partial unrolling mode. In that case, here we specify an unroll factor of 4, which copies the loop body code the factor number of times, and the result is something that resembles basically the code on the left. We also The compiler is also allowed to generate different kinds of codes, not exactly the same one. For instance, a common optimization, or how unrolling is usually implemented, is not checking the exit condition n every time. But if you know we are doing 4 iterations, we just execute this 4 iterations and do a reminder loop at the end of the code. So we have to less overhead to check the exit conditions of the loop, which can result in some performance speed up. We're also allowed to omit the unroll factor. In that case, the compiler can choose the unroll factor by itself. Usually, compilers today already implement some unrolling heuristic, even without a specific grammar, and use the cost model to determine what the unrolling factor is. Used to be. And using this syntax, we tell the compiler, hey, just use your unrolling heuristic cost model we already have. So we have not a specified unroll factor here. We can also omit the full or partial clause completely. In this case, again, it's up to the compiler to decide whether it wants to fully unroll or just partially unroll the loop. So what's unrolling useful for? First, we have the full unrolling, which is basically useful whenever you have a loop with a small constant trip count, which removes the loop. So I have no loop overhead at all. And the compiler can do something like instruction reordering to find a better order between instructions from iterations from loop body code from different iterations. This is basically only not beneficial if the L1 instruction cache is a bottleneck. But anyway, if the compiler detects that there is a loop trip count, it will unroll it probably anyway. So keep that in mind. It might be just doing it by themselves, but having this unroll full directives basically forces the compiler to do that. The other case is partial unrolling, which on modern x86 processors probably not as useful, since these have a very good branch predictor and allow instruction reordering from different instructions from different loop iterations. So at least I could not reproduce something where the unrolling would actually be beneficial. But for accelerators with less sophisticated pipelines, this might be still beneficial. For instance, from this paper called Optimal Loop Unrolling for GPU program, they experimented with different unroll factors for matrix-matrix multiplication compiled for an Nvidia processor. And as you can see, unrolling can give you a speed of a factor of almost 2, with different unroll factors giving different speed ups, where the optimum here, the minimum was an unroll factor by 2 of the middle loop and 16 in the inner loop. So it's not required that you only unroll the innermost loop, but you can basically unroll all of loops in there. So we covered unrolling, but we also introduced another directive, a tile directive. The tile directive, as far as I know, is not around in general purpose compiler. Just the OpenACC model supports a tile clause, which can be added to the loop directive to tell the compiler to tile this loop. We added the tile directive as a directive to OpenMP 5.1. And the tile sizes are specified by a sizes clause. This example, the tile sizes are tiles of sizes 8 by 8, which results in code which resembles something like on the right side. So with tiling, you always get twice as many loops as you had before. As an illustration, here have something like this. We have this case a smaller loop with 16 iterations, so 4 by 4 tiled into 2 by 2 tiles. And the output code you see on the bottom right is again 4 loops with the two inner loops iterating over iterations over a tile, so 2 by 2. sizes, and the outer loops iterate over the tiles themselves here. In this case, the number of iterations in each dimension is a multiple of the tile sizes. But what if this is not the case? In this case, we stay with 2 by 2 tiles, but we have an iteration space of 5 times 5. So in this case, we cannot fill every tile there, but instead we have some partial tiles where some tiles do not iterate 4 iterations, but just 2 or maybe even 1. The compiler, we made the choice in the specification that we allow the compiler to optimize this code in a way in that it can separate the code for the complete tiles from the partial tiles. So the main code for the hot code can stay out, can be more optimal in that there are not irregularities, in that it needs to check whether it's a complete tile or whether an iteration will execute at all. But it's a regular tile of always 2 by 2, which is beneficial, for instance, for vectorization. If you already know that the tile size is a multiple of the vector width, for instance, and it can execute the remainder in an epilogue after the loop, which, if you organize the code correctly, may not execute anything at all, because you may choose to have your data sizes be a multiple of your tile sizes. In that case, the special codes is nothing to execute, and you do not clutter your hot code that you want to run fast using conditions for just in case. So what does it help? I have here an example of Stencil for the heat equation in 3 dimensions. On my computer that I'm currently using for presenting, this executes in about 20 seconds. And if I do add some tile sizes, I can get it down to 14.2 seconds. The tile sizes in this case is 16 by 1 by 1024. This is just something that I tried out a bit. What's the fastest one? There are probably tile sizes that make it even faster than that one, but this was always just a low-hanging fruit. Experiment with tile sizes and get the code which executes the fastest. So in general, what it's useful for, as I showed before, it's good for if you want to localize your working set, optimize for a specific cache, for kernels that reuse some data multiple times, which is always the case for stencils. So stencils almost always benefit from tiling, but also linear algebra code in BLAS libraries such as the matrix multiplications. Other uses are if you want to split your workloads into chunks, such you have coarse-grained parallelism, or you want to use it as a preparation for other transformations, such as, even in the specification, we defined partial unrolling by first tiling by the unroll factor and then full unrolling of the inner loop. So this is also an example for transformation, composition of transformations. So we can combine tiling with other loop-associated constructs, such as the task loop. We can generally say loop-associated construct always applies to what's on the next line. So this task loop directive applies on the loop that follows there, the simple for loop in case of C++. But we can also apply it on the output of a loop transformation construct, in this case, the tile. This has the same effect as if you would replace the tile first by what tile would replace a loop, and then apply the task loop on the outermost loop, like in this case. Effectively, this has the same effect as a grain size clause that task loop already has, but we allow this construction allows it to apply in a much more orthogonal way with every loop construct, even for the loop literal loop construct, even if those do not have specific clauses to support this kind of coarsening. We can even apply a tile tiling on itself. So we have multi-level tiling. One tiling that optimizes, for instance, for the accessing the L1 cache, and another tiling that optimizes for, let's say, the L2 or L3 cache. And you see, writing the tiling tile parameters can be a lot more compact and easier to maintain than writing out the tiling manually. We can also do this composition using the unrolling. We first do the unrolling of a loop and apply a work sharing loop onto it afterwards. So we get basically a chunk size, but each chunk is guaranteed to be unrolled using the unroll construct. The unroll construct actually only allows follow-up transformation if you use partial unrolling. If it's possible that we do full unrolling, there's no guarantee that there actually is a loop, and we do not syntactically allow a follow-up transformation onto it. So this is a very nice example on how to split the optimization of some code from its semantics. We define what the code is doing using the host language. In case of OpenMP, it's Fortran, C or C++, but we do the optimizations in OpenMP by adding parameters. For instance, we can also choose different optimization depending on what platform we are optimizing for. So in this one, we can configure a software to either use target offloading or use the pthread-based implementation for CPUs, and choose different parameters using the preprocessor depending whether enable offloading is enabled, is set or not. With OpenMP 5.1, we also have the possibility to use a meta directive, which has inbuilt selectors for kinds of platforms. For instance, whether it's a GPU or CPU, what's the vendor and what's the model of your accelerator to use different, for instance, tile sizes. On this case, choose between either use tiling if you're compiling for a CPU, or use unrolling when compiling for a GPU. So let's go to a conclusion. So what's the intended audience of this is not the most general programmer, but specialists which know their hardware, who have an idea what the code should look like that that executes the fastest on a specific hardware. In this case, the workflow that I would imagine it would have is that first the application is written, maybe by a domain specialist. But once that's done, it's being profiled. So using different tools, tracers, that may also give you an idea what the bottleneck is, where the most time is spent, whether your application is bandwidth bound or whether it's compute bound. And then you can start applying low-hanging fruits, like the easiest thing if you have for a kernel a vendor optimized library, then use that one, or add some clauses like a schedules clause and specify a chunk size, which is best for the hardware, or what is now possible with OpenMP 5.1 as well, to use the unroll and tile directives to get some more optimization of your hardware. This is not meant as a replacement for really extreme optimization if you want to go down to the middle and write assembly code for the hardware. If you want to go that way, that's a lot of work to do. But this doesn't say the new OpenMP construct don't save you from that one, but it lowers this fruit from just applying unrolling and tiling, experimenting with it, try out different unroll factors and so on to get the best performance out of your code using relatively easy means. So this is not supported by any compiler for now. I'm working by myself on an implementation in Clang, which is under review at the moment. And since a lot of other compilers are based on Clang, I hope this is going to be inherited by other compilers as well. After the tiling directive, I'll also implement the unroll directive. But for OpenMP 6.0, I imagine we could have much more. For instance, most obviously more transformations such as loop interchange, loop fission and fusion, or even something as sophisticated as space filling curves. We may have auxiliary transformations which are not useful by itself, but may enable applying other transformations such as interchange that is only really defined on perfectly nested loops. We can add more clauses, for instance, clauses that control how the remainder loops for the tile and unroll directive are generated. And what I think is a large thing, which is very important to make it useful, is to apply follow-up transformations, not only on the outermost loop, but also inner generated loops. I have an example here on the top right where you apply tiling, and after tiling, you apply a work-sharing loop on the outer generated loop, but vectorization on the inner generated loop. Finally, we can also add something like semantics and optimization hints that just do not that are not prescriptive in telling the compiler what to do, but give it hints about the semantics of a program, for instance, like the IVDEP, whether code is vectorizable, whether it's parallelizable and interchangeable, or just instead of assumptions, just expectations that the compiler can use to optimize the performance. For instance, it's not necessary to invest time to optimize cold code. Thank you very much. This is my talk. I hope you find the loop transformations as useful as I do, and we may see each other around at this year's virtual supercomputing conference. Have a good day.